So in this short video, let's try and understand polynomial regression. So polynomial regression is a concept that is used whenever a data set is not linear in nature, which may be the case in most of the times. To overcome that case where a linear model just tries to underfit the data, we add some nonlinearity to our model. This is done by converting our features into some nonlinear aspect. I'll just start with it. As we can see here, data is non-linear in nature. The data points are non-linear in nature, and a single line is not able to capture most of it. So there is a high loss as well as a high underfitting for this case. So if we move on and we add some non-linearity. So here we make use of some features which are known as polynomial transformation. This basically transform our original matrix into a transform matrix. Which is usually given by phi 1, phi 2, and so on until phi k. We apply this and we get a new function. This is what I have mentioned before. If this is a linear model, it is not properly fitting the data. So we need something which has some curve. So we can have something like h w x equal to w naught plus w1 x plus w2 x square and so on. So here you can see our function is linear in terms of w or weights, but is non-linear in terms of features x. This is a bigger problem when we go to higher dimensions of data. In single dimension, we still can easily imagine, but as it grows, it becomes a great problem. As I've mentioned before, the underfitting problem is very high when we try to fit a linear model. And as we go on using the polynomial model, with higher the amount of degrees, the amount of overfitting increases. So that we have to find a sweet spot between the degree we want to use and underfitting and overfitting. So it should not go either way. So as we can see here, if we use a linear model, the training loss is quite high, whereas the validation loss is quite low. So this happens due to a small amount of the validation data. Again, to overcome underfitting, we can like increase the capacity of the model by adding more polynomial features or adding polynomial transformations to our data. The next slide, I'll show you. We first use a kth order polynomial transformation to create new features of the same original feature we have. So here, x is converted to x square, x cube, and so on. So if our model was earlier a linear model, now if it is a 2-degree model, we have something like this. For a 3-degree model, we have something like this, and so on. So as I again mentioned before, here our function is still linear in weights and non-linear in our feature. We can simply write it as a form of a summation equation. Again, phi is denoted by something like phi naught, phi 1 until phi k, where each component denotes a specific transform to be applied to the input feature. So we can simply write it in form of vector multiplications or transpose of weight vectors into polynomial transformation. So here are like a few examples how the data gets converted. So for a single feature, if we have only one feature, then we get to the power k into the power amount of vectors or the new features. Whereas if we increase the number of features, we have more number of features. So we have x1, x2. Here in this case, we have x1 until k. Okay. So and here if since there are two, we have here again one we write it as by default one x1 x2 one x1 square comma x2 square. We also have x1 x2 and so on as we increase the power. So here it is 2-degree polynomial, it is 3-degree polynomial. So in this case, again we are getting this x square into x1 square into x2 term. So this is how it will keep on growing as we increase the amount. While implementing it in Python, we make use of SQL library. We have a direct library function that we can use polynomial features, and we can define the degree we want, and it will give us the new features. And then we can simply use model linear regression model to identify the new results predictions. Yeah, now we can see one more thing, how the fit changes as we change the degree. So as you can see, if the degree is zero, there's a flat line. With increasing degree, it gets some slope. Then at m is equal to 3, it has two curves. And it goes on. And as the degree increases way too high, here we can see it is trying to fit each and every data point on our data set, which is going towards overfitting. To avoid this, we can do one thing. We can make use of regression, lasso regression or ridge regression. I'll discuss it in the next slides. So this is like adding penalty to our model, so that reduces overfitting. So as we have seen, 0 to 1 is underfitting, 3 and 4, 3 and 5 seem to be reasonably fitting, and 7 and 9 seem to be overfitting. Here, if we plot root mean square error, we can easily visualize how the training and validation losses behave with the increase in degrees. So if we see here, when it is overfitting the data, the training loss is very low, which is quite obvious, and validation loss is very high because it has learned each and every point and it does not know how to predict for new points. Whereas somewhere here on degree 3, we are getting both the losses to be quite low. So this would be the sweetest point in our polynomial degree which we would like to consider. Similarly, we can try for newer models when we try and execute or identify new models. For examples. So issues with polynomial regression. Higher order polynomial models are very flexible, or in other words, they have higher capacity. So basically, they are overfitting. They can overfit easily. Hence, they are prone to overfitting compared to lower degree polynomials. Perfect fit to the training data, but poor prediction accuracy and validation data. This is obvious because it has learned each and every point in our training data, so it is going to struggle for newer data. Choosing larger data sets can easily overcome overfitting at to a certain point. And then there is newer methods which we call regularization or penalty methods, which avoid overfitting on smaller data. So, if we have a larger data, you can see the curve shifts in a more smoother way. Whereas if we have lower data, it is trying to fit each and every point over here. Then fixing overfitting through regularization. Overfitting is caused by larger weights assigned to a higher order polynomial. So if say W1 is having a very high value, then it is saying that X1 is of the highest importance, and other features are going into very low amount of usability for the model. So what we try to do is we add a penalty term, and this will control the behavior of our model. So regularization modifies the loss function, which leads to the change in derivative of the loss function, and hence changes the weight updation rule in our gradient descent. So since this is the weight updation rule, this comes by solving a very simple equation. But as of now, we can remember this as it is very easy to remember. So here in this case, this is y dash. Y dash is our predicted value. So it is basically y dash minus y into y dash minus y. Again, this is transpose, and this is one normal. So this is how it is. Uh, so here there are two types of regularization techniques that we use: L2 regularization or ridge regularization, L1 regularization, and lasso regularization. So this is called L1 because the penalty term is a single degree term. It is a summation of W weights, and this is summation of W square. So that is why this is L2 and this is L1. And elastic net is a combination of both of these. So we can see here in the ridge regression, this term gets added. Now this is a regularization constant. So lambda is like a hyperparameter that needs to be tuned by the user, and that can be chosen by seeing how the graph is behaving, the loss graph. We can do that while practically making use of it. So here we can see that it is W transpose W. As we move ahead, as I've mentioned, for lasso it is summation of W, and that is how it. So this is how polynomial regression works, and I hope you understood the concept. It is easy. It is a basic concept in machine learning, and it tries to overcome the problem of linear models, whereas to overcome the problem of polynomial models, we use regularization terms to add penalty to our models, which avoids overfitting. If you like the video, do share, like, and subscribe to